Hey folks, recording the next video for you here on vibrational spectroscopy. So I've already got some information written down here on the board. This is a review of what we came up with back, I think, I want to say from like day 15 or something like that, day 16. And so if you recall the harmonic oscillator model, we use Hooke's law here, negative kf, force constant times displacement. Recall displacement is the difference between the equilibrium bond length and the elongated bond length. Okay, so R minus RE. And you calculated that in one of your take-home exams. Okay. And so from there, based on the fact that force is negative dV dx, we come up with the potential energy operator, 1/2 kfx squared. We plug this into the entire Schrodinger equation. So our kinetic energy operator and our potential energy operator gives us the total energy. And the solution for that was E of nu, which equals nu plus 1/2 times h bar omega. And omega is the oscillator frequency. And we remember nu is our vibrational quantum number, 0, 1, 2, 3, etc. So I'll rewrite this equation. I'm just in a slightly different way to be consistent with our wave number notation. So, this gives our solution in joules. So our wave number solution, I'm going to write as G of nu with that little tilde to indicate its wave number. And that's going to go nu plus 1/2 times nu tilde. Okay? So if we just compare these two equations for a minute, we recognize that h bar omega is a frequency. It is an energy, okay? And so here we have, here we have an energy, a frequency and energy, okay? And so the equation for the vibrational energy goes, and this is in wave numbers, right? So it's going to go 1 over 2 pi c and then times the square root of kf divided by mu. So it's very similar to this oscillator frequency, but it's got that factor of hc built into it, and the 2 pi, right, was absorbed from the h bar right there. So it's got that factor of hc to give you the wave number solution. So just like we said with rotational spectroscopy, we have two different equations. One's the Joule solution, one's the wave number solution. So we're predominantly going to stick with this solution right here. Okay. And so our selection rules must have permanent dipole moment. Hopefully you remember that from OChem. Okay. And then also delta nu can only be plus or minus 1 for the perfect harmonic oscillator model. So, and if you recall with our statistical mechanics, because most molecules, 99% or more, are in the ground vibrational state, almost all IR probes the fundamental transition. So I'll write that the same way I wrote that with our rotational notation. So that's nu from 0 to 1. So almost all vibrational spectroscopy only probes that one single transition. Okay? And so if I go and think about what an IR spectra is, I'm going to write that as delta G. Okay? And so that's going to be G of nu plus 1/2. Or excuse me, G of nu plus 1, because we recognize that the quantum number can go up by 1, minus G of nu, right? So this is my going from the 0 to 1 transition. So if nu is equal to 0, right, G of 0, and then G of 0 plus 1, G of 1. And if we did that on this equation, you would find that just equals that constant right there. Okay, so in an IR spectra, unlike in a rotational spectra, the peak that we see, the one peak we see, directly gives us the value of this equation, which contains the force constant, which contains the reduced mass, and within that force constant, we could actually get the bond distance or the displacement out of that. Okay, so now our perfect harmonic oscillator model looks like this purple equation, right? It's like this very simple parabolic. So I posted another short video for you all, which I think goes into the Morse potential with a little bit more detail. And the Morse potential is what actually happens. So there's going to be differences in the energy levels calculated from the Morse potential versus the harmonic oscillator model. And so I'm not going to spend a whole lot of time getting into that. But from using this Morse potential, I'm just going to rewrite this G equation, okay? Which is going to go as nu plus 1/2 times nu tilde, so that's still the same, okay? And then we recognize that we have we recognize we have anharmicity, which is related to the fact that this Morse potential is not perfectly symmetrical. Okay, so I'm going to write down that equation. So that in the same way distortion led to a decrease in energy levels in the Morse potential, that this type of anharmicity also leads to a decrease in energy levels in the Morse potential. So that's going to be minus also nu plus 1/2 squared times xe times nu tilde, where this xe is our anharmonicity fit. Okay, so this is typically an experimental parameter, something that you determine experimentally. We can come up with an equation for it, which goes as the following: a squared times h bar all over 2 mu omega, and that's the same as the following: nu tilde divided by 4 times d e tilde, okay, where this dE tilde is the depth of our energy well. So this dE value is the value from the bottom of the well all the way to the top. So I'll write that as dE, okay? And note that that is different than the value D0. Let's see, did I indicate a D0 value here? So I didn't indicate a dissociation value, but write comparatively. So I'll call that value D0, which actually starts at the first energy level. So that's the dissociation energy to split the molecules apart. But this dE, that's the depth of my Morse potential well, which is that constant right there. So you can get these from fitting spectroscopy data, which you're going to do in Spec 2, and I'm going to review that momentarily. Let's see here. Yes, I'll talk about that momentarily, but we could calculate it, you know, if we had a more detailed way of calculating this Morse potential. Okay, so I'm going to go ahead and switch slides here, free up some room. All right, and I'm not going to talk about various, bends and stretches and so on in the same level of detail that you do in OCHEM. So in OCHEM, you guys go in really big detail into all of those types of stretches and so on. I'm only predominantly going to talk about a couple of these because I think you've done these. So the first one I'm going to talk about is water. Okay, and if I draw a cartoon water molecule here, okay, there's 3 stretches, and these stretches and bends are based on the relative motions of atoms to each other. Okay, so when this oxygen nuclei moves down and the 2 hydrogen nuclei move in, so kind of something like this, if I can do it, okay, we call that the symmetric stretch, often abbreviated as VSMM, okay? And for a free isolated gas phase water molecule, that's 3652 wave number, and that is definitely IR active. And it's IR active because it does result in a dipole moment with the way this molecule, with this nuclei moving down. So as each of these hydrogen nuclei move in towards the oxygen nuclei, it forces the oxygen nuclei to want to move away. And that does, in fact, result in a dipole moment. Okay, so we have the, and I'll compare that to the asymmetric stretch. Okay, so I'll draw an elongated bond here and a shorter bond here. And what ends up happening with this stretch, the concerted motion, is as this nuclei moves away, it influences this nuclei to move closer, but at the same time, it also influences that oxygen nuclei to move away. So you have kind of something that looks like this, okay, for that asymmetric stretch. All right, and that's often noted as VASYN, okay, V asymmetric. And for a free isolated gas phase molecule, that's slightly higher in energy, 3756 wave number. All right, and so then the final that we have is the bend, okay? So here the bend looks like this. And the bend is now if the nuclei moves down and these nuclei move away from it as a result, that creates this kind of bending, wagging motion, if you will. So bend or the wag. And that occurs at a significantly lower energy, V bend, and that's at 1595 wave number. And so all three of those are IR active, okay? And so these are three, what I'm going to call normal modes, all right? So what if we look at now CO2? So that's another popular one. So we can look at the symmetric stretch, okay? And now in the symmetric stretch, because CO2 is linear, as these two nuclei move apart, it doesn't affect that carbon nuclei, okay? And so what that means is the symmetric stretch of carbon dioxide, even though we can calculate that it would be 1388 wave number, this is not IR active. So I'll put a big check next to all of these. That is IR inactive. It doesn't change the dipole moment, okay? But certainly the asymmetric stretch of CO2 does, okay? So as these two nuclei move closer, it repels that nuclei, and so you'd have this asymmetric stretch occurring, and so that's VASM, and that is going to be 2349 wave number. And this, principally, this is the major stretching of CO2. It's the major sink of IR energy. So when we talk about CO2 as a greenhouse gas, this is the principal vibration that absorbs the brunt of that energy, okay? And so there's a couple different ways. So there's two different ways you could do the bend or the wag with CO2. So one is if we move them in this orientation, right? Again, kind of like you're flapping your wings right here. But there's actually a degenerate mode. And that's if I look at it, you know, at this angle, suppose that the nuclei moves this way, then these nuclei will move that way, okay? So those end up being very low energy and what we call the fingerprint of the IR spectrum, 667 wave number. And so that gives us 4 normal modes, 1, 2, 3, 4, and only 3 of them are IR active. So there's an equation that we can come up with to calculate the normal mode. I'm not going to derive it, but I'll describe a normal mode. It's an independent synchronous motion of atoms or group of atoms that may be excited without leading to the excitation of any other normal mode. So in other words, when I stimulate the symmetric stretch in water, it will not stimulate the asymmetric stretch. If I shine exactly 3652, only this stretch will be activated. Okay? So each one of these things that I'm putting down here, I'm going to put a tilde over them, right? Because what that means is each one of those normal modes has a different force constant. Okay? So all of these are corresponding to the 0 to 1 stretch, each and every one of those normal modes. So there's an equation for linear molecules and nonlinear molecules. And for linear molecules, that goes as 3n minus 5 normal modes. And for nonlinear molecules, that goes as 3n minus 6. So for example, water is a nonlinear molecule. And so this is the number of atoms. Okay? So given that water has 3 atoms, 3 times 3 minus 6 equals 3. So we predict the 3 normal modes from those equations. So CO2 is a linear molecule, and it also has 3 atoms. So 3 times 3 minus 5 gives me 4 normal modes. So we can do this with all molecules, except for, let's see, it doesn't necessarily predict which ones will be IR active. We have to see a permanent dipole moment. Okay? So I'm going to keep going here. I'm going to clear up some space. And so, I should have erased that because I wanted to keep talking about water IR spectra. Well, I'm already committed anyways. So I'm going to erase this, and now there's a spectra I'm going to show you here in a moment. Okay. So here, and I'm going to come back to the spectra a couple times. Not this one, but this one rather. So here, I just kind of got these from the internet. I've got a couple of spectra to show you. The first one that I want to focus on is down here in the right corner because it has only condensed phase, so liquid or solid. And I want you to see the effect of what happens when you change the isotope. All right. So you can see H2O, there is under this region between 3,000 and 4,000, that would be the combination of our symmetric and asymmetric. And that's why I had you do that exercise for Spec 1, deconvoluting the symmetric and asymmetric stretches. Okay? That's why it's pretty wide. Well, if I replaced one of those H's with a D, the effect is that it's narrowed, but the energies are pretty similar. Okay? And if we look at the bending region, all right, what are we looking at here? Excuse me. So there ends up being a big separation between symmetric and asymmetric stretches when you have HOD versus H2O as well as D2O, right? You can really see how pronounced that becomes. So if you look at the H2O region, this region right here, this is just symmetric and asymmetric, okay? But now if I look at HOD, the symmetric and asymmetric really become separated by putting a D in there. And then now if I look at D2O, you can see here there's like some little shoulders here. So these are the symmetric and asymmetric for D2O. And you can see that's why you'd want to do that deconvolution, right, to tease out where those symmetric and asymmetrics are occurring. And now way down in this region, you can see the bending region, and you can see the effect that has by putting deuteriums on So that really changes the force constant quite drastically. So now if I look up here, and we'll talk about what the vapor lines here in a moment, but if I compare liquid water to ice, you can also see a big difference associated from the symmetric versus asymmetric stretch. So in liquid water, there's pretty much even populations of symmetric and asymmetric. And that really makes sense when you think about it, because they're tumbling all over each other, right? They've got that hydrogen bonding network that's free to change. But if you look at ice, ice is very rigid, and ice doesn't have that same flexibility as liquid. So the relative populations between symmetric and asymmetric are no longer even. And you can see, so the asymmetric stretch is the higher energy. So that this shoulder right here in ice, that would correspond to the asymmetric. And this large peak right here would correspond to the symmetric stretch. And if you kind of think about it in a sample of ice where it's all rigid, it kind of makes sense that the material would want to swell symmetrically. Okay, and I'll talk about what this vapor is here in a minute. Okay, so back to the slides. So now I want to talk about rho vibrational spectroscopy. And I gave you a short video on that already, so I'm just gonna kind of touch on a few things here. Rho vibrational spectroscopy is the same thing as gas phase FTIR. Okay, so in a liquid and in a solid, you cannot stimulate the rotations. The molecule is sterically hindered. It can't rotate in this like lattice. But in a gas, it's free to rotate and vibrate. And as I just described earlier, the quantized ice skater, right? You start bringing your hands in and you rotate fast, and you bring them out and you go slow, and you bring your hands in. Okay, so that's basically what we have going on with gas phase FTIR. It's impossible to not stimulate the vibrations and the rotations at the same time. Okay, so our combination becomes the following. I'm going to say S tilde as a function of nu and j, and that equals our G wave number solution to the vibrational model, and our F solution of J to the rotational model. All right? And so that looks something like this. Nu plus 1/2 times nu tilde. Remember, that's the quantum numbers, 0, 1, 2, or 3. That's the actual energy of vibration in terms of wave numbers. And then times J plus 1 times B. Okay? So when we have a nu plus 1 from a nu, J changes by plus minus 1. Okay? So again, we can't stimulate a vibration without stimulating a rotation. And so what ends up happening is the following. Delta S of nu and J. So that's what we would observe, right, in the spectroscopy, the change in that energy level. And that equals the following. S nu final J final minus S nu initial J initial. Okay, so that's going to be our spectra. And so we end up getting 3 categories from this situation. We get a situation where we have nu plus 1. So nu goes to nu plus 1. And delta J changes by negative 1. Okay. We have a situation where we go nu to nu plus 1. And delta J does not change. And then we have a same situation, nu goes to nu plus 1. And then, of course, here delta J changes by plus 1. Okay. This, where J goes down by negative 1 is called the P branch. Where J does not change, that's called the Q branch. And where J goes up by plus 1, that's called the R branch. So PQR, -1, 0, +1. Okay? And so I'll write this as nu of P. Okay? I'll write this one as nu of Q. And I'll write this one as nu of R. And if we were like live in class, I would have you derive these equations. I'm just going to cut straight to it, okay, and give you these directly. And so because nu is changing by the same amount each time, then we don't need to actually worry about its dependency on nu. Nu is always going up by +1, so we only need to worry about these dependencies in terms of the j's. And so what we would do is we would plug in each of these equations into the initial and final and carry out the differences, all right? And I've got that worked out in my notes if you want to see it. So for example, this would be the function of s, and it would go nu +1 and j -1, for example. This would be, so this function right here, right? And so this would be nu +1 and just j, and this one would be nu +1 and j +1. Okay? So when we do that, we get the following. I'll write them up here. So nu of p of j, the p branch, this will go as nu minus 2 times j times b. And because we have several j's populated, so when j is equal to 0, it's just nu. When j is equal to 1, it's nu minus 2b. When j is equal to 2, it's nu minus 4b, etc. So we get nu minus 2b, nu minus 4b, nu minus 6b, etc. And just like we saw with pure rotational spectroscopy, there's going to be a difference of 2 times b for each of these lines. A 2 times b difference in each row vibrational line. Okay. The Q branch, as a function of j, just ends up equaling nu. Okay? Because since j doesn't change, all it does is just give you a single line. All right? And then for the R branch, as a function of j, okay, that goes as 2 times b times j plus 1. Oops, hold on a second. I think I wrote something down. Oh, okay. It goes as 2bj plus 1 plus nu. All right? So when j is equal to 0, it's just nu. When j is equal to 1, let's see here. Oh, yeah, excuse me. So when j, I got that wrong. So when j is equal to 0, it's nu plus 2b. When j is equal to 1, it's nu plus 4b. And then when j is equal to 2, it's nu plus 6b. So once again, you would see spacings every 2 times b. Okay? So in a spectra, what you would have, if I plot this absorbance versus wave number, and here I'm going to put like 4,000 wave number on this side and like 500 wave number on this side. Okay? So we would only see certain molecules with a Q branch. So I think I maybe forgot to mention that. There is a selection rule for Q branch. Where did that go? Oh, yes. Aha. Okay. So the only time you get this as an allowed transition is if a molecule is paramagnetic. Okay? So typically doublets, things that have a doublet electronic spectrum, so an unpaired electron. So things with paired up electrons do not have a Q branch. Okay, so this is allowed only for paramagnetism. Okay, so a typical gas phase IR spectrum would look like the following. So we would see, if we had a Q branch, we would see it, let's say, right here. But if we didn't have a Q branch, we would see a bunch of lines, just like we saw with rotations. Okay. So I'll draw a couple of these. So this, at the higher energy side, would be my R branch, because it's J plus 1. It's increasing the energy. So I'll put a dotted line right here to say this would be Q if it existed. So this has got to be the R branch. And then my P branch, because it's J minus 1, it's decreasing the energy. So that would look like the following. Okay. And you might have noticed, perhaps, that these will take on each a Maxwell-Boltzmann distribution, but they will be mirror images of each other. So we can still calculate the same J max based on the temperatures, just like we did with rotational spectroscopy. Okay, so now I'm going to switch and I'm going to show you some real gas phase FTIR spectra of two molecules, HCl. Actually, I should say three molecules, HCl, DCl, and carbon monoxide. And these are spectra that were acquired. Oh my gosh, sorry, I'm all over the place. So first, let me finish talking about this graph right here. So we talked about liquid and ice, and then now we can see this is the water vapor lines. These would be the rotational lines. And you notice it looks chaotic. It doesn't look like this nice symmetrical picture that I drew. And the reason for that is because within these vapor lines, you would have a R branch and P branch. I think I just realized on my notes I wrote R twice. I wrote R and I said P. So just to make sure we got it, this is P, okay, to the lower energy side. So what you would have here within this region, because you have the symmetric stretch and the asymmetric stretch, you would have an R and P branch for both the symmetric and asymmetric stretch. So that's why this looks quite chaotic. But luckily it's well resolved from the liquid. So like the liquid, if the liquid had a Q branch, right, they're occurring, maybe somewhere around here and somewhere around here, like the center of those peaks, the vibrational numbers. So now the Q branch and P branch, there's actually two of them for each symmetric and asymmetric line. So that's why these vapor lines get chaotic. And on that spectra I gave you that you fit for Spec 2, you might have noticed at the tail end there's all those crazy lines. Those are actually the water vapor lines, because if you think about it, if you're taking a spectrum of liquid water, you're also going to take a spectrum of its vapor, as the water is evaporating like into the IR beam. Okay, so now let's look at the classic HCl and DCl. And I want you to notice the scale here. It starts at 3100 wave number and goes all the way down to 1900 wave number. So this is a sample that PChem last year did. I regret that PChem this year can't do it because we're all trapped at home. But this is actually synthesizing HCl and DCl in the gas phase simultaneously in a low pressure device that can go into the FTIR spectrometer, and you get some fantastic looking spectra. So here we can see R branch. Here you can see the Q branch is missing because HCl is not paramagnetic. And then here we have the P branch. I highlighted a couple of the peaks here. So you can see this peak has an energy of, this one is 228, 64, and then this next peak is 2843.7. So if I calculate the difference between those, let me do that really quick. 2843.7 minus 28, oops, I did it backwards, that's okay. So that gives me 21.2, and we note that, right, each of these spacings are 2 times B. They're always going to be 2 times B apart. So each one of these peaks is 2 times the rotational constant. So if I divide that by 2, I get 10.6, and that's a really good value for the rotational constant. But now look, if I compare something way out here, like I'm going to compare the difference between this peak and this peak, okay? So I get, so 2651.8, 2651.8, so that's from right there, minus 2625.7, I get, now divide that by 2, I get 13.5. So these are supposed to be every 2 times B, so they should be exactly 2 times B apart. So these two were 10.6 apart, but these two were 13 wave numbers apart. And that's once again due to the centripetal distortion. So as we get out to higher and higher J's, right? This is like, you know, the J1, the J2, the J3, the J4, etc. As we get to those higher J states, the centripetal distortion is really taking over. And so the levels get spread out as we go down this way, and they get crunched together as we go this way. And so if we were to put a value, so, you know, we can expect then that this peak that I'm going to say here and this peak that I'm going to say here, those will be 4 times B apart, where halfway between would give me exactly that vibrational energy, which would give me the force constant, etc. So now you notice over here, these set of peaks, here's DCL. And so the way the synthesis works, you make DCL and HCl at the same time in the same reaction vessel. And you can do it because they're both really well resolved in their spectra. So again, if I were going to calculate the Q branch of DCL, it's like somewhere right here. And you can see DCL is, you know, let's say around 2100, where HCl is around 2900. And that's because HCl has a significantly larger force constant than does DCL. So in other words, the reduced mass between HCl is bigger, right? The mass difference is much bigger between the H and the Cl versus the D and the Cl. There's something else that's observable in the DCL spectrum that's very cool, and it's present in the HCl spectrum. You just can't resolve it as well. But if I zoom in, I'm going to draw a box around just the R branch right here and blow it up. And now you notice that there's 2 peaks associated with each one of these transitions. And those are actually the isotopes. So remember, in a sample of chlorine, about 75% is Cl35 and about 25% is Cl37. And so it happens that in the DCL spectrum, those isotopes are easier resolved. And then you can actually see them. So this is really, really cool. So you can see that, like, this whole family of peaks, this peak right here, this would still be the J1, but this is the J1 for a D35Cl, and this is the J1 for a D37Cl, which is really, really cool to see those isotopic abundances. We rarely see those in spectra, but they're actually resolvable in this FTIR gas phase spectra, which again is super cool. And then the last one I want to point out to the spectrum, you see this small little thing going on right here. That's carbon dioxide. So the students that recorded the spectra didn't get all the carbon dioxide, the basically atmosphere, ratioed out. And you notice carbon dioxide even has a R branch, P branch, and a missing Q branch. So the reason why this is smooth looking and we don't see the individual rotational lines, because the rotation constant for CO2 is incredibly small. It's really, really tiny. It's so tiny we can't resolve it in this spectrum. So each of these peaks are just really smooth. So let me back up here for a second. Undo. Okay, so now I'll just throw my cursors down over here for a second. And I'm going to get into the how the IR works in a lot more detail in the coming lectures. But let's see if I can have these separated by one. Yes, they're separated by one data point 2046 and data point 2047. And you can see that's roughly 1 wave number different. So each of these are different by 2372.1, 2373.1. So that means the rotational constant for CO2 is less than 1 wave number. So we can't even see it. But all the same, we didn't quite get all the CO2 out of this spectrum, and it still has, and it's a gas, so it still has that observable R branch and P branch. So the last one of these gas phase IR spectra I'll show you. This is for carbon monoxide, and you can see that, so it would have appeared right on top of the DCL. So this is a separate spectra, and someone just used a cylinder to get this CO2 spectra. Let me go ahead and get it out of this. Yeah, so I'm going to blow this way up. So you can see now the CO spectra, its B constant is much, much smaller than HCl, and that makes sense, right? Because it's a triple bond compared to a single bond. So that triple bond can't elongate as much as the single bond, okay? And I think you calculated that in exam 2 even. And if I go and I compare these two values, right, we know that these are supposed to be 2B apart. And so I have 2139.3 minus 2135.4. That gives me 3.9. So divided by 2, that's 1.95 wave number for the B constant. And you can definitely tell that they're getting crunched together. You can even see and hear. These are actually related to some overtones that was talked about in the previous video. But again, the point of this is to show you that the B constant is much, much smaller than HCl. And that makes sense because it's a much stiffer bond. Okay. So now I'm going to switch over to talking about what you're going to do for Spec 2. So this is a handout that's in the Spec 2 assignment, okay? And this is going to walk you through, like, how to, it gives you all of these nice equations that we talked about that you can review. So it kind of goes into much more detail with respect to, like, centripetal distortion and harmonicity, etc. And I think that was talked about really well in that other short video that I posted, okay, that I want you to watch. So it talks about, right, this Morse potential versus the harmonic oscillator. But what you're actually going to be doing for this as we scroll down here, okay, so again, it shows you the nice P branch, Q branch, and R branch. They have what's called the M values. And you notice here the way this works, they're giving you what's referred to as the J double prime values. And the J double prime values are the values that originate from the ground state, and the J prime values are in the new excited state. So again, this is the new equals 0 state, and this is the new 1 state. The J double prime correspond to the ground vibrational state levels. The J single prime correspond to the vibrational excited state levels. And so you notice the way that that goes here on the P branch, that's going to refer to J double prime for 1, because since it goes to -1, it has to go from 1 to 0. But then on the other side, it starts at 0 because it's got to go up. It's got to go from 0 to 1. In any event, to make life a little easier, we use what's called these M values, these index values, where starting on the R branch, okay, it goes 1, 2, 3, 4, 5, 6, 7. And then starting on the P branch, it goes -1, -2, -3, etc. And we can come up with this equation, equation 9 and equation 10. I think equation 10 is the equation you want to use. And this is designed to be a linear regression. So if you plot the peak values, and this is the spectrum, this spectrum right here, this is the 2019 spectrum that you're going to use. So you're going to first start by taking this cursor. So for example, if I put a cursor there and I put a cursor there, let's think about this for a second. So here now, these are the lower energy values. So these are the first two P branch values that I've highlighted. So my first two P branch values, that would be -1 and -2. So what I want to do is create a table of values where I'm going to say this circle right here, right, my A cursor, that has I'm going to look at the energies, the wave numbers. So that A cursor is 2864.9. I'm going to write, first I'm going to clear some space on my whiteboard, and I'll show you how you're going to start collecting this data for Spec 2. Okay? And it's a shame the 363 folks couldn't do the synthesis. It's a really, really cool synthesis. So under high vacuum, you drip con D2SO4. So you drip 17 molar deuterated sulfuric acid over a sample of sodium chloride, and it bubbles and it fizzes and it's super violent and it liberates DCl in the gas phase. And there is a very small amount of hydrogen proton contamination, so that's why it also liberates HCl in the gas phase. So it's too bad they couldn't do it. But in any event, so these first two peaks that I've indicated here, so I'll start writing M values and nu values. So this one would be my -1. This one would be my -2, right? -1, -2. So my -1 has an energy of, so that's the A cursor, 2864.9, 2864.9. And then my B cursor is 2843.7, 2843.7. Okay, so I'll switch over to my whiteboard so you can see what I'm doing, right? And I'd have -3 and -4 and -5. So you get all of those values going, okay? And then if you notice here on this equation, right? This equation is nu as a function of m equals all of this stuff. So I'm going to go ahead and copy that equation down, and I'm going to switch over to my whiteboard so you can see what I'm doing. Okay, minus 2 alpha E times m, let's see, m squared minus 4DE m cubed. So so let's see here, and if I go to this equation, you can see that I guess it's not quite a linear regression. It's more of, it's a polymeric, right? This is the equation of a polynomial. So now here I've got that equation written down. So if you plot these nu values on the y-axis and the m values on the x-axis, you're going to get some kind of like an equation, right? Each one of those dots corresponds to each one of these points. And you'll do a custom fit in Igor, right? So fit equation. And that fit equation will give you, so you notice here that the y-intercept, right, will correspond to that nu 0 value. And then now you notice that here goes m, m squared, m cubed. You can think of those as the x's. So all of these will be your fit parameters, okay? So then you notice here that you'll have a direct parameter for alpha and you have a direct parameter for DE, but you don't have a direct parameter for BE. So if you call all of this whole thing, let's say A, and this B, and this C, right? When you take A, we'll do some algebra here, right? And you can solve for what the rotational constant has to be, okay? So that describes all of this. Follow through. I want you to also work on the isotope effect because we have DCL data. So read through this on the isotope effect, and that will take you through Spec 2 really nice. So you've got everything you need to go ahead and start Spec 2. So I would go ahead and get that going. Okay, folks, I'm just going to keep recording lectures. Have a good one.